Here's problem 3028. Each of two parallel wires separated by 6 millimeters carries a 40 amp current. These two currents are in the same direction. Determine the magnitude of the magnetic field at a point that is 5 millimeters from each of the wires. Let's have our two currents come out of the page towards you, and then it'll be easier for us to graph where these magnetic fields are. So they're going to be coming out in the z direction towards you. Here's 3 millimeters up on the y-axis and 3 millimeters down on the y-axis. So our first current, I1, which is 40 amps, is coming out of the page towards you, and our I2 is also coming out of the page towards you, 40 amps. Then we have a point on the x-axis, point P, where we are exactly 5 millimeters away from each of these wires. So we truly have ourselves a 3, 4, 5 triangle. And at these points, if we use the right-hand rule for the current I1, point your thumb in the direction of the current, then there's going to be a magnetic field along this radius of 5 millimeters, tangent on that radius, B1 going counterclockwise, and likewise for I2 it's going to go counterclockwise as well along the radius of this, so it's going to be going, B2 is going to be going up like this. The angles for our 3, 4, 5 triangle, if we consider this our 3, 4, 5 triangle, let's call this angle theta and its complementary angle alpha. If that's true, then with this right angle here, and alpha being one of those angles, that means that this angle here, that goes all the way up to B2, is theta, and that would mean that this lesser angle right here is alpha, and this angle right here, with the alpha 9 degrees adding up to a supplementary angle, that angle is also going to have to be theta. So we're going to have our two magnetic fields at point P extending outward from the x-axis, equal in magnitude, up from the x-axis at respective angles of theta on either side. So the x components of these two magnetic fields are actually going to cancel out. We have a B1x that's going to be equal to a B2x and in opposite directions, so they will cancel out. And we'll only have to worry about our y components, B1y and B2y, which are in the same direction. And those two y components will add, giving us a net magnetic field that is in the y direction. So that's where we're headed. The magnitude of these two magnetic fields are the same. So that's going to be B1 equal to B2, which is going to be mu naught I over 2 pi r for an infinitely long wire, which is mu naught 4 pi times 10 to the minus 7 times the current, 40 amps, over 2 pi times 5 millimeters, 5 times 10 to the minus 3, and the 4 pi divided by the 2 pi will leave us with a 2. The 40 divided by 5 will leave us with an 8. So that's be 16 times 10 to the minus 4. So this is going to be equal to 1.6 times 10 to the minus 3 Tesla. And as we said, our Bx is going to be equal to B1 cosine theta minus B2 cosine theta. B1 and B2 are the same, so is cosine theta. So we have no x component. our By is actually going to be equal to 2 times B sine theta, because we have these two components that are exactly the same adding together. That's going to be 2 times 1.6 times 10 to the minus 3 times the sine of theta. Now if we look at our original yellow 3, 4, 5 triangle, the sine of theta is the opposite side over the hypotenuse, which would be 4/5. So the sine of theta is going to be 4/5, and that is equal to 2.56 times 10 to the minus 3 Tesla. And as we've drawn it, it would be in the positive y direction, just as the way we've set it up here. But the magnitude of that magnetic field is 2.56 times 10 to the minus 3 Tesla.